An assertion from teacher Carlos stresses Durham School. I've committed my whole vocation to taking part in an unambiguous theory about the universe. Then, unexpectedly, this happens. The theory is being checked. I acknowledge this demand since it is through such perception that we gain ground and push ahead in science. The James Webb Space Telescope is basically disturbing a few long-held convictions in cosmology that have been viewed as truth for quite a long time. Another ultra-rare picture has uncovered that we have committed errors in space science. The telescope, which was intended to uncover the focal stars of the universe, is indeed disrupting the past. This point of view could introduce a totally new, legitimate perspective. Not all analysts are deterred by these new disclosures. Numerous researchers are inviting these progressions since it has for quite some time been certain that there were blemishes in our past suspicions. The irregularities in estimating the universe's pace of development alone ought to have raised warnings for any researchers quite a while back. As opposed to straightforwardly addressing these worries, many grip to old hypotheses. The cosmic microwave background radiation, CMB, the most old light known to man, was conformed to 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to form stable hydrogen molecules. This progress, known as reionization, made the universe transparent to light. The CMB was first identified in 1964 by American physicists Arnold Penzias and Robert Wilson while they were working with new radio gear. They experienced a steady clamor coming from all bearings. This revelation was at first thought to be major evidence for the theory of the universe's starting point. Penzias and Wilson were awarded the Nobel Prize, and their discoveries turned into a vital foundation throughout the entire history of space science. The CMB probably gives a brief look into the early universe, with small temperature fluctuations offering basic bits of insight into the circumstances not long after the Big Bang. Researchers involve the CMB as a dependable marker to gauge tremendous parts of the material universe, including the universe's pace of extension. Edwin Hubble had proactively made such estimations in the late 1920s. He saw that far-off systems were receding from us in all directions, and that their speed was corresponding to their distance, a relationship now known as the Hubble law, or the Hubble constant. Despite the way that Hubble's estimations were not as exact as they may be today, they were significant when the CMB was found. Specialists recalculated the pace of extension, viewing it as extensively lower than Hubble's underlying evaluation. Subsequent recalculations utilizing type Ia supernovae as standard candles gave a more precise check. However, disparities remained, and the distinction in extension rate estimations has been recognized since the 1990s. Specialists hypothesize that there may be issues with the CMB data analysis methods or the possibility of general relativity itself. This disparity, known as the S8 strain or Hubble tension, suggests that our interpretation of the universe may be fundamentally flawed. Since the James Webb Space Telescope, JWST, began its operations, it has provided surprising data that could help resolve the issue. Galaxies so old and advanced that their formation might have begun before the Big Bang are challenging old scientific assumptions. Space science is now confronting what is viewed as the greatest predicament in modern cosmology. The pace of extension of the universe and the speculations of how things came to be are under intense scrutiny. New pictures reveal a universe that veers off decisively from past models. The S8 tension has acted as an early warning, with specialists still adhering to old theories, now wrestling with the realization that how we interpret the universe may be inadequate. This uncertainty has left numerous analysts feeling frustrated and dispirited. To address this crisis, we must understand how science works. Theoretical researchers use a mix of mathematical models, observational data, and logical thinking to arrive at conclusions. Their knowledge comes from identifying anomalies, experimental results, and theoretical investigation. The term theory itself suggests enhancements and contemplations, rather than conclusive facts. Our experimental data comes from images provided by telescopes, sound waves and radiation detected by radio telescopes, as well as data from neutrino and gravitational wave detectors. The James Webb Space Telescope allows us to isolate the most ancient light into individual frequencies and observe it in unprecedented detail. It can uncover what elements were present in distant galaxies billions of years ago, the mass held inside them, and the number of stars they contain. However, the Webb's pictures might have limits. For instance, it can't effectively identify galaxies or black holes that produce nearly indistinguishable brightness due to gravitational lensing. Our understanding has progressed to consider different potential outcomes, often dismissing alternative explanations. New discoveries from the James Webb Space Telescope offer pivotal clues that could lead to replacing old theories with new insights. Researchers are now facing these discoveries, which appear to be so exceptional that finding new explanations is proving difficult. The latest findings are shaking the foundations of physics, causing concern among many scientists. The principles of physics today are still largely influenced by Isaac Newton's 17th century work. For a long time, his laws of motion and gravity have provided the foundation for understanding reality and the universe. Newton's laws work perfectly under normal circumstances on Earth. However, in space, his ideas were extended to an extraordinary degree, achieved by Albert Einstein during the 20th century. Einstein's special theory of relativity, published in 1905, changed how we interpret reality, showing that the laws of physics are relative to the observer's motion. His general theory of relativity, published in 1915, extended these ideas with mathematical descriptions of gravitational phenomena, accounting for the curvature of space-time caused by masses like stars or galaxies. While Einstein's theories were validated in various areas, he recognized their limitations and sought a unifying theory. Without progress, no researcher has yet succeeded in this pursuit. It is fascinating to consider where the errors could lie. Michio Kaku, a renowned American astrophysicist, suggested that solving this issue could lead to a Nobel Prize. We truly need to explore what reality could have been misunderstood, he stated, whether there have been misinterpretations of anomalies, or if the very telescopes may be to blame. Dark matter and dark energy are two of the biggest mysteries that scientists are trying to unravel. These elusive substances make up about 95% of the universe, yet their exact nature remains unknown. Dark matter is believed to be responsible for the gravitational effects we observe in galaxies, while dark energy is thought to be driving the accelerated expansion of the universe. Despite their profound influence on the cosmos, both remain largely invisible, detectable only through their indirect effects on visible matter and the curvature of space-time. The James Webb Space Telescope, with its advanced capabilities, is expected to play a crucial role in probing these dark components. Its ability to peer into the distant past of the universe could shed light on the formation of galaxies, stars, and possibly dark matter itself. However, these revelations may also challenge our fundamental understanding of physics, leading to a rethinking of some of the most established theories in cosmology. As more data is collected, the scientific community is faced with a pivotal moment. The discoveries made by the Webb telescope might require the revision of long-standing theories and could open the door to entirely new fields of study. The challenge now is not just to interpret the data, but to expand our frameworks of understanding in order to accommodate the complexity and surprises that the universe continues to present. The journey ahead is not without its difficulties, but it is a time of immense opportunity for scientific discovery. As researchers continue to push the boundaries of knowledge, they are not only exploring the cosmos, but also re-evaluating the very tools and theories that have shaped our view of the universe. The work of the James Webb Space Telescope could mark a turning point in our understanding of the cosmos, leading to profound shifts in both science and philosophy as we confront the unknown. In the end, the pursuit of knowledge is a continuous process of questioning, revising, and rethinking. With each new discovery, we come closer to answering some of the universe's most profound questions, but we also encounter new mysteries that will require future generations of scientists to explore. The quest to understand the cosmos is a journey without end, and with each step, we uncover deeper layers of reality that challenge our imagination and expand the horizons of human thought. Prime suspects in the cosmological quandary flow models recommend that dark matter and dark energy together account for no less than 95% of the universe. Yet, neither has been directly observed or proven to exist. They may not exist at all, or perhaps have properties we don't yet comprehend. One possibility being examined is that dark matter's qualities could have evolved over time, possibly displaying some type of intelligent gravity, which could exert an influence through mass or space-time. However, it has not been conclusively shown to behave as expected. In any case, the reality of space-time curvature, as outlined by Einstein, has been supported many times. We cannot completely dismiss the possibility that gravity has exceptional properties or that another force is causing gravitational attraction. Over time, certain constants in cosmology and astronomy have been established as central standards, recognized as reliable due to their consistency. Measurements suggest that slight variations in these constants might offer new insights into the universe, potentially revealing anomalies without dark energy. It is also possible that our interpretations of light shifts have been incorrect, leading to mistaken distance estimates and errors in calculating galaxy ages. Perhaps our assumptions about the universe's conditions were flawed, or we misunderstood the cosmic microwave background radiation. It might even be that the universe does not originate from a single starting point, challenging the Big Bang theory. Minor errors in the James Webb Space Telescope or other observational instruments cannot be ruled out. Experts and researchers acknowledge that mistakes in instrumentation, data handling, or interpretation are always possible. The ongoing reassessment of cosmological theories highlights the strength of the scientific method, the ability to adapt and refine our understanding based on new evidence. The James Webb Space Telescope's discoveries are more than a technological leap. They represent a significant moment in our quest to uncover the universe's deepest secrets. As we grapple with these revelations, it is crucial to consider the broader context and implications of such fundamental shifts in cosmology. This process is often driven by the need to refine theories based on novel observations. The discovery of unexpected anomalies in established theories can be unsettling, but it also presents a critical opportunity for intellectual growth. Theoretical models in cosmology are designed to provide a coherent framework for understanding the universe's origins, development, and evolution. However, as new data emerges, these models must be tested and, if necessary, adjusted to accommodate new findings. One key area of focus is the nature of dark matter and dark energy, which are central to contemporary cosmological models. Dark matter, an invisible form of matter that does not emit or absorb light, was proposed to explain discrepancies between observed galaxy rotations and the mass predicted by visible matter alone. Similarly, dark energy was introduced to account for the observed acceleration of the universe's expansion. Yet, despite their primary roles, both dark matter and dark energy remain elusive, with research on Earth still failing to directly detect them. This has led experts to explore alternative explanations and potential theories. The challenge of understanding dark matter and dark energy is further complicated by the vast scales involved in cosmological observations, including distant galaxies, cosmic microwave background radiation, and other large-scale phenomena, which offer indirect evidence of these components but remain mysterious in their exact nature. This uncertainty has prompted scientists to consider a range of theories, from modifications to existing models to entirely new paradigms. Some theories suggest that dark matter could be composed of more exotic particles than previously believed, or that dark energy represents a completely new fundamental force. Another fascinating area of cosmological study is the investigation of cosmic inflation. This theory proposes that the universe expanded rapidly in its earliest moments, leading to the large-scale structure we observe today. While inflationary theory has successfully explained many aspects of the universe, such as its homogeneity and flatness, it also raises questions about the nature of the inflationary period itself. Insights that challenge established models of expansion could lead to revisions in how we understand the universe's early history. Finally, the search for extraterrestrial life remains a driving force in space exploration. The discovery of exoplanets, planets orbiting stars outside our solar system, has opened new avenues for studying the conditions necessary for life. Advances in telescope technology, such as the James Webb Space Telescope, allow us to examine the atmospheres of these exoplanets for potential biomarkers. The possibility of finding life beyond Earth carries profound implications for how we interpret the universe and our place within it. In conclusion, the reassessment of cosmological theories reflects the strength of the scientific method. The James Webb Space Telescope and other advanced scientific instruments have provided remarkable insights into the universe, prompting experts to revisit and refine long-held theories. This process of continuous inquiry and revision is essential for advancing our understanding of the universe and addressing the fundamental questions at the heart of cosmology and astronomy. As we continue to explore the universe, we remain engaged in a quest for knowledge that seeks not only to answer key questions, but also to inspire future generations to push the boundaries of human understanding. As we keep advancing our understanding, new discoveries will undoubtedly challenge our existing models of the universe. The James Webb Space Telescope represents a significant step in this journey, providing scientists with the tools and data necessary to delve deeper into the cosmos. Its extraordinary capabilities enable unprecedented observations, offering insights into the earliest galaxies, stars, and cosmic phenomena that were previously inaccessible. The implications of these discoveries extend far beyond the realms of astronomy and cosmology. As our models of the universe evolve, so too will our understanding of fundamental forces such as gravity, dark matter, and dark energy. Each breakthrough provides an opportunity to refine our theories, making the scientific method more dynamic and responsive to new evidence. This process of inquiry and revision, rather than being a sign of failure, is a testament to science's ability to self-correct and advance. As humanity continues its exploration of the cosmos, it is clear that we are only at the beginning of a profound journey. The interplay between observation, theory, and innovation drives our understanding of the universe forward. Each discovery, whether it confirms existing theories or challenges them, brings us closer to answering some of the most profound questions about the nature of reality. Key among these questions is the ultimate fate of the universe. Will the expansion of the universe continue indefinitely, leading to a big freeze, where galaxies drift so far apart that stars eventually burn out? Or could it culminate in a big crunch, where gravity eventually reverses the expansion, collapsing everything back into a singular point? Alternatively, could the mysterious force of dark energy alter its behavior over time, leading to scenarios we have yet to conceptualize? Another critical avenue of exploration lies in the origins of the universe itself. While the Big Bang Theory remains the dominant framework, emerging data from telescopes like the James Webb Space Telescope may provide the granularity needed to refine, or even rethink, this paradigm. Understanding what happened in the earliest moments of the universe, including the dynamics of cosmic inflation and the role of quantum fluctuations, holds the key to unraveling the secrets of existence. Moreover, the search for extraterrestrial life raises profound philosophical and scientific questions. Discovering even the simplest forms of life beyond Earth would fundamentally shift our understanding of biology and our place in the universe. The identification of habitable exoplanets, combined with the ongoing search for biosignatures and technosignatures, marks a new era of astrobiology. These efforts not only deepen our knowledge of life's potential diversity, but also challenge us to consider the ethical and societal implications of such discoveries. At the same time, the development of next-generation telescopes and instruments, such as the Square Kilometre Array, (SK), and the Extremely Large Telescope, (YLT), promises to revolutionize our ability to observe the cosmos. These advancements will enable us to peer deeper into space and time, uncovering structures and phenomena that were previously invisible. Coupled with advancements in computational modeling and artificial intelligence, scientists are now equipped to analyze vast datasets, revealing patterns and insights that were once beyond human capability. Beyond observational cosmology, theoretical physics continues to push the boundaries of our understanding. String theory, quantum gravity, and other emerging frameworks aim to reconcile the apparent contradictions between general relativity and quantum mechanics. The unification of these two pillars of physics remains one of the greatest challenges of our time, as it holds the promise of a theory of everything that could explain all fundamental forces and particles in the universe. As we progress, interdisciplinary collaboration will become increasingly vital. Cosmology, astrophysics, particle physics, and even disciplines like philosophy and computer science must work in tandem to tackle the complex questions that define the field. The synthesis of ideas from diverse fields fosters innovation and ensures a holistic approach to understanding the cosmos. Ultimately, the journey of exploration is as much about the questions we ask as it is about the answers we find. Each breakthrough, no matter how small, expands the horizon of human knowledge and inspires us to look further, question deeper, and strive for a greater understanding of the universe. As we stand on the precipice of discovery, the future of cosmology and space science promises to be as boundless and awe-inspiring as the universe itself.